linear functions or linear graphs. Okay, linear means the line, right? That's a line, but not everything is linear. Some things are exponential. Exponential has got sort of a curve to it. They're not the same as quadratics, but they grow, okay? And they grow at a certain rate, all right? Now, let's look at a very basic graph of an exponential. Let's say it's y equals 2 to the power of x, 2 to the power of x. So notice the variable is in the exponent now. And let's make a quick table here, x and y, 0, 1, and 2. When you put 0 in for x, y becomes 2 to the power of 0. Do you remember from maybe earlier in the course when you did exponents what 2 to the power of 0 is?
1.
There's 1, good. And then what about 2 to the power of 1? What does that mean?
2.
2, good. And then 2 to the power of 2 is 4. Now let's go one more. Let's put 3 in. What's 2 to the power of 3?
9 or 6.
Okay, so that's where I provide a little bit of explanation, right? This means 2 times 2 times 2.
Oh, so 9.
Try again.
6? Oh, I'm so dumb. I don't know how I did it.
Don't say it. Don't be critical of yourself. This is one that is mistaken all the time. 2 times 2 is 4. 4 times 2 is 8. Now, what do you notice about from going 1 to 2, 2 to 4, 4 to 8? What's the rule? What's
it's
the
jumping.
rule?
Oh, wait, it's not.
It's multiplying by what number?
2.
And then multiply by 2, multiply by 2. So what would 4 be?
16.
You got it. Okay. Now a really quick sketch of this. 0, 1, 1, 2, 2, 4, 3, 8. Do you see how this thing is growing
Yeah.
pretty quickly? Okay. That is an exponential. Variables in the exponent. All right. Have you seen this before?
Yeah.
Okay, that's good. All right. So there are two types of exponentials. There are growth and there are decay. So how do you determine the difference? I'm going to give you some examples. So let's say the equation is 0.5. Sorry, let me put that wrong spot. Let's say it's 2 to the power of x. This is an example of growth. Okay, but 1/2 to the power of x, that's decay. Okay, let's say it's 3.5 to the power of x, that's also growth. But 0.035 to the power of x is decay. Okay, and let me give you one more here to think about. 1.001 to the power of x is growth, but 0.999 power of x is decay.
What about a negative? Would a negative be decay?
Good question. Good question. So I'm going to answer that here in a moment. The general form of an exponential is like this: PA to the power of x, or sometimes you see it as PA to the power of t. If a is greater than 1, it's growth. If 0 less than a less than 1, it's decay. Basically, if it's between 0 and 1. So the negative would be here on the P. You would never see a is never positive or negative. I'm sorry, it's never negative. It's only positive. That's what I meant to say. Okay. So let me give you some problems here. Let's say it's y equals 3 times 0.2 to the power of x. Is this growth or decay? You're just looking at this number here.
Decay. Right?
Yeah, you said decay? Yes.
Yeah.
Okay. Now, what if it's -3 to the 0.2x? It is still decay.
Yeah.
It has nothing to do with that number here. Okay.
What if it's like -3 to the power of x? Is that decay?
Okay.
Because it's less than 1.
Good question. So really good question. Keep in mind that a is bounded between 0 and 1, so you have to sort of manipulate this. And we'll do that now. Negative 3 is really negative 1 times 3 to the power of x. And you can apply that exponent to both of these. So it becomes negative 1 to the power of x times 3 to the power of x. Okay, something like that. Now, you generally don't see this ever. You never see a negative here because what happens with this is it alternates. Negative 1 to an even exponent is 1, but negative 1 to an odd exponent is negative 1. So you might wonder, well, what does that even look like graphically? Well, it bounces. You'll have a point here, and then a point here, and then a point here, and a point here. So you won't see that as, I guess, the short answer. You won't see something like that, but it is a good question. Is that confusing?
No, I don't think so.
Okay. That's actually a really good question. I like what you're doing here because it's, you want to know, you're like, well, what's going on? So let's say it's 1.1 times 0.9 to the x. Is this growth or decay?
Decay.
Decay again, right? Okay. Now let's look at a much simpler example. We know that 2 to the x is growth. But what if it's 2 to the minus x? Do you remember from earlier in the course what negative exponents do to this number?
Does it make that number negative?
It does not. It has nothing to do with the sign.
Oh,
So let's take a look at this. 2 is really 2 over 1 to the negative x. The negative will flip the exponent.
oh,
Or I'm sorry, flip the base. It flips the base. I said exponent. It flips the base and it becomes like that. So 2 to the minus x is really 1/2 to the x power, which is decay.
oh.
Let's look at another example here. Let's say it's y equals 5 over 2 to the negative x. Currently 5 over 2 is 2.5. That looks like growth. But the negative exponent means to flip it. So this is really 2 over 5 to the power of x.
So it's decay.
So it's decay. Now I can add in some other things. I can put in negative 500, 1/3 to the power of negative x. This negative 500 has nothing to do with whether it's growth or decay. It comes down to what's inside parentheses after you deal with the negative. So in this problem, you have to flip the exponent there. And now you can say whether it's growth or decay. What do you say?
Oh.
Is growth or decay?
Oh, that's growth.
Growth. Very good. Okay. Next thing that you might see here is 1.5 3 to the minus 2x power. Okay. Actually, let me not do that. That's too complicated. So let me just find some practice problems here real quick to go through. I got some pulled up here. You're just going to tell me growth or decay. Actually, these aren't very good. Let me get another moment here to find some. Do you typically use a calculator in your class?
We can, yeah.
You can. Okay, that's good. All right. Well, I'm struggling to find what I want, so we're gonna transition to a new topic here, which is I mentioned earlier that you can there's a lot of these population models that they'll give you. They'll say the population as a function of time is the amount that you're starting with times a to the power of t. Okay, it looks really complicated, but they give you most of the values. They give you the initial population, and then a depends on whether it's growth or decay. If it's growth, a equals 1 plus r, and if it's decay, a equals 1 minus r. Okay, so we're going to look at a problem here or two to try to understand this better. Okay, So let me snip something in here. The first year of a charity walk event had an attendance of 500. That's the initial amount. That's your P0. The attendance increases by 5% each year. This is your rate. Okay, the word increases tells you that it's growth. Okay, so we're gonna start our equation. P of t equals, this is P0, 500 is P0. A, because it's growth, is 1 plus R. Now you don't use the 5%, you have to convert 5% to a decimal. Do you remember how to do that?
Yeah.
Okay, what is 5% as a decimal
I
then?
think just 0.5.
That would be 50%.
Oh, 0.05, sorry.
Good, good. Okay, so it becomes 1 plus 0.05 to the power of t. Okay, so we're using this equation up here. They're giving you P0, okay, and they're saying, okay, it's 500 times 1 plus 0.05, and we can add those together. So it's 1.05 to the power of t. Do you have a scientific calculator available? Not your phone. Your phone won't be very useful, will not be very useful for this.
Can I just look up scientific calculator on Google?
Okay, let me send you one that I like, that I think will be something that we'll use a bunch together here. I drop it in the chat. It's a Desmos Scientific.
That was the one I
What
was gonna use.
Awesome. All right. Didn't have to convince you. So I want you to find P of 0. So that means to take, go ahead and write, and in the way with the Desmos Scientific, you don't put this P of 0 in, you're at the right hand side. I want you to type in 500, 1.05 to the power of 0. Tell me what that becomes.
100, 1.05 to the power of what?
0.
Uh, 500.
500, and that's what we expect. That's the starting amount. Okay, so we're not surprised by that at all. The next thing is, why don't you do it for 5 years later? Like, how many people do we expect at the charity walk in 5 years? Now, because it's people, it's humans, can't have half a human, at least alive. Round to the nearest ones place. Ones place for me, please.
638 or 639. Probably
639. Perfect. Okay. Awesome. All right. Does that kind of make sense how we set that one up?
Yeah.
Any questions on this? Because I'm going to have you do one like it now. I'm going to have you write the equation for this next one.
Okay.
Questions?
No.
Okay. All right. I wouldn't give you something that you couldn't do. This is not like, it's not like in class where they give you one that's totally different. It's just different numbers. So I want you to just write the equation for me, please.
34,000.
Okay.
Open bracket. 0.025.
Okay.
Wait.
There's something that goes here. We can scroll up and look if we need to.
Scroll up. Wait, is it your starting salary? Your company is 34,000 in it. I don't know.
Let's go back and look. So what did I say about A here? What is written on the right here?
1 plus R.
So if it's growing, it's 1 plus R. You have the R, but you have to add 1 to it.
Oh, so is it 1.025?
Yes. And we're missing a variable. Where does the variable go?
At the end, the exponent.
Yes.
X.
So I like it.
P.
T generally is used for that. Okay. So, and by the way, this is awful. Maybe it's fine if you're 18, but and 2.5% isn't even inflation. So this is a terrible problem because it's not even realistic. But you need your salary to at least increase by inflation, or you're really in bad shape. So what I'd like you to find is how much the person can expect to earn in the 10th year, please. and round to 2 decimal places because it's money. We know that that's reasonable.
34,000. One. Um, 38,460. 7.86.
We're doing in the 10th here, right?
Oh, wait. Oh, 10th. I did to 5.
Okay.
Same thing. Just 43,522.87.
And most salary increases are by percentages, especially at larger companies, Fortune 500 companies. At smaller companies, they may be in dollar amounts, but nevertheless, it's something to consider. Okay, so a new problem here. We're going to look at some problems here where they're going to introduce a year in them. So we'll take a look at this. All right, in 2010, an item cost $9. I'm trying to think of something that cost $9 back then, but it says the price increases 1.5% each year. All right, so don't worry about the fact that it's 2010. Just treat that as what's called the base year, but you don't have to do anything with that. I want you to first write the function for me, or to give me the function verbally for this.
$9.
Okay.
I mean, $9 in open parenthesis. 1.15.
That would be 15%.
Oh, 1.015.
Yes. To the power of
X.
X. I'm going to use T just because I like T. All right. So we're interested now in 2030, but T, you got to be careful. T is not the year. T is the number of years since 2010. Okay, so in 2030, how many years has it been?
20.
Since two. So in 12, I'm sorry, in this question here, in 2030, T is 20. You're going to use that value in for T. So go ahead and calculate that for us, please.
All right. 12.12.
Okay. Very good. All right. So just kind of to close out here, we got at least time for one more question. I want to give you problem kind of like it's like the last one we just did, number 12 here. But all I want is your final answer for part B. Just want to know the answer to part B. So you got to do A, but I'm looking for the answer to part B. And imagine I'm just going to grade whatever you put in the box here.
2.5. Is it 788? Wait, 7,888.
Yes, very good. Okay, so let's look at another problem here together. We'll look at just a quick decay problem because things do go down. We don't necessarily think of like population decaying, but they do. Money also decays. You might see that or heard your parents talking about that in the stock market. So when you decay, when you decrease, it's 1 minus r. So in this problem, it's 1 minus 0.1. So you start with 2000, but it's 1 minus 0.1 to the power of t, or 2000 times 0.9 to the power of t. Something like that. Now, did you say you had seen this before?
I think I have.
Great. Well, believe it or not, we are at the end of our lesson for today. We'll just stop a minute or so early just because I'm not sure what else to do. We can't really get into a new topic, but really, really well done. Again, if you have the ability, please send over something at a time.
Yeah.